Hello, welcome to the first lecture. I'm Spesi Lamakatini. This is my email if you want to contact me, and this is my office, which probably after the pandemic you will be able to find me in. So I'll be taking you for the next segment of this course, specifically Introduction to Radio Astronomy. And in this first lecture, I'm just basically gonna tell you why we do radio astronomy, and not maybe any other frequency. So let's get started. Okay, first let me just clarify what we mean by radio waves. So this is electromagnetic radiation. So they'll have an energy of E is h nu, where this is Planck's constant. Planck constant. And that's the frequency, which you can relate to, so the frequency is also c over lambda, that's the speed of light. And that's the wavelength. Okay. So in radio, you can go up to 1 terahertz or 1 giga or 1,000 gigahertz, or in wavelengths like 0.3 millimeters, and you can go as low as 3 hertz, and that's basically in the extremely low frequency range, which is given by this here. So that's and basically on the lower end of that in frequency, you can go up to 100,000 kilometers. So this low end is limited by quantum noise. Basically, it's a combination of this equation and the uncertainty principle. Combination of this and uncertainty. And basically, but we will never get there with ground-based telescopes, because you will be limited by the atmosphere before you get there. So the atmosphere is only transparent above 10 megahertz to radio waves. And another good thing about radio waves is that the intergalactic gas and dust is mostly transparent to radio waves. Also, the galactic. I think I got that incorrect. Let me write that again. It's the inter and the intra. Galactic gas, and then the same thing. A bit more on the atmosphere. So this is a plot that shows you the opacity, how opaque the atmosphere is as a function of wavelength. And as you can see, it's like almost completely opaque to gamma rays, ultraviolet, and X-rays. And there's a small gap of visibility for what we call the optical part of the spectrum, or visible light. There are patches of visibility for infrared, but it's mostly also blocked. But then we have this huge gap for radio waves. So then we have a case where we can see through our atmosphere, but also we can see through the clouds of gas and dust. So radio is very advantageous because of these facts. So it's one of the most interesting parts of the spectrum to study, and we will basically do a basic course on how to measure these radio waves using different techniques. Okay. Let's have a look at some of the more important science results from radio astronomy. One of the first ones was the non-thermal radiation from our galaxy. I think this non-thermal radiation was synchrotron. From our galaxy. You also have like AGNs, So basically, this violent universe, this powerful force of radio galaxies by known as black holes called AGN, or active galactic nuclei, AGN, and we were able to actually. I think about it was 2 years ago when the EHT was able to make an image of our supermassive black hole, basically the one at the center of our galaxy, but ours is not active, right? Otherwise, I don't know what implications that would have for life on our galaxy. There's also thermal spectral line emission from coal gas. One of the major examples is of course the hydrogen line, which is the most abundant element in the universe. So it's just good to be able to measure it, to trace it, to study its dynamics, and radio is the wavelength in which you can do that with extreme precision. You also have continuum emission from stars and pulsars, neutron stars as well. There was the detection of the cosmic microwave. The cosmic microwave background, which basically was a one of the major pieces of evidence to support the Big Bang theory. We also found evidence for dark matter by studying the rotation curves of galaxy, basically seeing how the hydrogen moves in those galaxies, and strong gravitational lensing, which in a way the image from EHT, if you remember this, image from EHT EHT image of black hole event horizon. That's one example of strong lensing, but maybe an extreme case, but a case nonetheless. Okay, so yeah, these are some of the major, and of course there's way more than this, but you only have a finite amount of time to go over all these things. And then finally, let me just end with this nice image of Cygnus A. So Cygnus A is one of the brightest things in our sky, and basically what you have a supermassive black hole here at this point, and then because this the nucleus, the black hole is the nucleus is active, so it shoots out these jets which go out in opposite directions, and they interact with the medium. Could be gas, cold gas, or warm gas, and as they interact with this medium, they form these huge lobes, right? And basically, from that interaction, you have more synchrotron emission coming out. Some can be seen in X-ray. That's the blue. So the blue is X-ray. You have the radio is pink, and the rest of it is optical, which is, I suppose, is that yellow or orange? It looks more orange, like it's a mixture of yellow and orange. So that's optical. Yeah, this is a picture. Basically, you can see the image credit here. You can look for it if you wish. But yeah, so as you can see, the synchrotron emission stretches very, very far out compared to the size of the galaxy where all the energy and all this power is coming from. This is actually one of the most extraordinary things about radio astronomy, is that like the host of the energy is much smaller compared to the scale of the emission that you see. So we will see many more examples of this as we proceed with the course. Then finally, let me just give you a plan for this part of the course. So you're going to study first radio telescopes and radiometers, starting with the short dipole antenna, which also is called a Hertz dipole, I think. Hertz dipole. Then we're going to study the antenna power or illumination pattern, sometimes also called the primary beam. Okay, we're going to study the antenna power gain and aperture, not apertures, just, I suppose you can say apertures, yeah. And then apertures and angular resolution. And then finally, we're going to study system temperature, or I should say system temperature and telescope sensitivity. Telescope sensitivity. Okay, then in the second part, we're going to go into radio interferometry, just the fundamentals. We're going to start by going through aperture synthesis, which is basically a way that tells you how to form one unified aperture from a set of smaller antennas. Then you're going to go on to asking how do you then form an image from all these disconnected antennas, and how you then weigh each antenna with respect to others in order to manipulate the image to look like something that you like, but which is still representative of what the true brightness is. Then you're going to go into brightness reconstruction, then eventually to signal propagation, basically studying the effects that would affect your signal as it moves. Say you have some source here, your signal will move through layers of the atmosphere, and then it will go through the primary beam of your antenna to whatever the receiver element is, and all these things will affect. So this is the path of the signal, and basically each of these things will have a gain, basically that will be added to the signal, and this gain will corrupt the signal in some way. So we're going to study this process in some detail, which will lead us to the rhyme. So this is the rhyme, or the radio interferometry measurement equation. Probably one of the most important equations in radio interferometry, and also one of the most consequential one in recent times. And then when we've done with that, we're going to go through calibration basics. And for the assessment for this part, there will be 2 sets of tutorial. Each will be accompanied by a spot test. So in the spot test, you'll be tested on the material from the tutorial. Okay. And then I will give you CAT7 datasets, images basically, from which you will be expected to extract flux densities and spectra. And I will only accept submissions in LaTeX. If you don't know what LaTeX is, it's time you want to start now to learn what it is and learn how to be proficient in it. Okay, and then finally there will be an exam at the end of the course. And so this is me for this lecture, and you'll hear from me again in the next one.